Меня слышно? Меня слышно?
Раз, два, три. Слышно вроде бы.
Я тоже тебя слышу. Хорошо.
Да. Нет, но качество звука оставляет желать лучшего, но ничего не поделаешь.
Я не понимаю, в чем дело. Вроде бы это один мой знакомый говорит, что проблема с наушниками, но я не понимаю, ни у меня, ни гарнитура. То
Нет,
есть
но
это
есть две
именно
вещи. Есть, во-первых, микрофон в наушниках, а второе, в зуме можно включить original sound. И это сильно улучшает качество.
original song.
Ну, у тебя Windows или Linux или что? Добрый день.
Добрый день.
Мгм. Ну вот у вас очень хорошее качество звука, в отличие от Миши Вялова. Не знаю почему.
Да, я с телефона захожу, потому что...
А,
Ну, я
интересно.
захожу из-под андроида, с планшета, и, казалось бы, должно быть тоже хорошо. Вот поди ж ты.
Yeah, Peter, hi, we see you, but don't hear you.
Voice too. Okay. Now
Yeah,
you hear
and
me.
now we hear you.
Yeah. I may need to leave before the end because there is a seminar at BU at the
Yeah,
same
no,
time.
no, we
But
are happy to see you even for
but
a
but
short
but
time.
so will there be a video of this?
Yeah, always, no, unless there is something wrong in Bordeaux University, which never had happened yet.
Okay.
We have the videos, and Misha Raskin send the link, and I copy and then put it on YouTube.
Good. Good.
Oh, hello.
Hello?
Yeah. So we can hear you and see you.
Yes? You can or cannot hear me?
We can, we do.
Okay, good, good,
Yeah,
good.
sorry.
Okay.
Sorry for the confusion.
So,
Yeah, yeah, yeah.
hi, Matt. I haven't
Oh,
seen you
hello.
for
Oh,
a
nice.
long time. Oh, so man. Where is my something happened here.
Yeah, so this is all recorded. I guess no, if nobody is against, then we will post the recording in the YouTube as we usually do.
Uh-huh. Okay. Hi, Davide.
So today we have quite unusual talk about this mystery of artificial intelligence. So probably we should be ready not to understand any proofs or whatever, but it's but it's a mystery which deserves to be.
Well, it's interesting that at least what I see from the abstract, Matt is using the same example, what to learn, that was somehow the favorite example of Ray Solomonov also, whenever he was thinking about learning algorithms.
Well, I think you'll find my thinking much simpler than Solomonov's thinking.
We'll see.
That's a good thing, because you never really, I guess, can understand exactly what Solomonov was saying. So it's simpler is better. Okay, so should we start now, or we are waiting for someone specifically? So I guess we can start now. Will you try to share some screen?
Yes, I will, and I think it will work because
Let's try it then.
Because it worked 10 minutes ago, so so we'll see if it works now. So yes, so I'm going to try to share a blackboard, basically.
Now we see a black thing.
Oh, here it comes. Ah, yes. Yes, so
now we see gray rectangle inside the black one.
A blackboard where I can draw for you.
Okay, good.
Okay, so the first thing. So first, I would like to show you how to add binary numbers. So you may think you already know how to add binary numbers. I thought I knew how to add binary numbers. But if we just are given some numbers to add, I should make them line up at least. So now I'm going to show you a way which I hope feels different, because I would have thought, how many ways are there to add binary numbers? I know how to add binary numbers. It can't be very different. There can't be a very different algorithm, because you would get a different answer. And if I want to get the same answer, I'd better do pretty much the same thing. So I'll just show you this algorithm, and you can decide for yourself if it feels similar or different. Okay, so the algorithm, it has 3 passes, but each of the 3 passes is trivial. Okay, so the first pass, we just identify the columns where the two rows match. So, right, I'm just highlighting each column where the 2 rows. Right here we have a 0 on the top and the bottom. Again, a 0 on the top and the bottom. Here, a 1 on the top and the bottom. I'm skipping everywhere where it doesn't match. Okay, so these are where the 2 rows match. Now, if you're using a pencil, you can't highlight like that. So what we'll do is we'll just put a little dot to mark those positions. Right, so this is the first pass. So I'll say that I call the algorithm dot copy fill. It's the dot copy fill algorithm. And right now, as you might guess, we're doing the first of the 3 passes, which is the dot pass. We're putting dots at each place where the 2 columns match. And so I hope I did it correctly. Okay, and then also, well, clearly there are infinitely many leading zeros on both rows, so we could put dots out to the left. I'll just put 1 to remind myself about that. And we also have infinitely many trailing zeros on the right-hand side. I'll just put a dot over there instead of putting infinitely many dots. Okay, so anyway, that was the dot phase. It's very simple. Now, next we proceed to the copy phase, which is also very simple. So the dot phase goes forwards, the copy phase goes backwards and the fill phase goes forwards. So the three passes just are like a zigzag, and then you finish. Okay, so how do we copy? So now we consider only the dotted positions, the dotted columns. So, for example, in this column, we see there's a 1 above the dot. Here, this column has a 0 above the dot, and so on. Okay, so we're going to copy these values from the, and we're just considering the dots. We copy each value to the next position. Here we had zeros, so we put a 0 here. We had zeros at this position, so we put a 0 at the next dot. Here, that dot had
Why the
ones.
first 0 is on the left? It should be somehow under the last digit, no?
This one? Or this
Yeah,
one?
this one.
So this one had the 0 from the previous previous dot.
Yeah.
So we copy from dot's column to the next one. So
Yeah,
in
but
this
the
column
first
we have
0
one.
is
This first 0 is from over here, the invisible zeros,
yeah, but why we move it 2 positions?
because we go to the next dot. We only consider the dot position.
Ah, to
So
the
here,
next dot we go. Yeah, sorry.
ones,
Yeah.
yes. So these ones are going to get written right over here.
Mhm.
We put a 1 there. That 1 goes here. The 0 goes here. The 0 goes here. It's pretty simple, right? We just copy. That's why I call it the copy phase, because we're copying the digit. Okay, and then finally we have to fill all these gaps. So we're left with these gaps. We need to fill them. How do we fill them? Well, we fill each gap with the opposite of the leading digit, right? So this gap has the 1 as the leading digit, so we fill it with zeros. Right, the next gap had a 0 as the leading digit, so we fill it with 1s. And so on. A 1 is followed by zeros, a 0 is followed by 1s, a 1 is followed by zeros, a 0 followed by 1. Okay, there. And now we're done. That's the sum. That's how you add two binary numbers. Or that's how I do it now. I used to do it differently. I used to do it in a complicated way, which involved complicated operations like adding single bits, and maybe which produces a 2-digit answer. I don't know. I think you would have to be at least 10 years old to understand that. But I think this algorithm you could learn at 5 years old, because each of the operations, dot, copy, and fill, doesn't even require understanding addition in any way. They're very trivial operations. And so I like this algorithm. Also, this algorithm is clearly symmetric in the digits 0 and 1, right? Whereas the traditional algorithm is not symmetric in the digits 0 and 1. So it's not even obvious that addition is symmetric in the digits 0 and 1 the way we learned it. But if we would learn this algorithm, it would be obvious, completely obvious. Addition is perfectly symmetric in the digits 0 and 1. Yeah, I like this algorithm. The first person I showed it to said, "Oh, that's a bad algorithm. It's much faster to do it the old-fashioned way." And then they tried doing a big addition the old-fashioned way, but of course they got confused somewhere about the carry bit and they made a mistake. Whereas this algorithm, it's really, you can go back and spot check it, right? We can go back and check every step that was done, right? We can check the dots are in the right places. We can check that each of the 3 phases was done correctly. All the evidence is there. So that's how the algorithm works. I hope it was clear. I can do many more examples, but I hope it's clear how it works. So I was very happy to find a new algorithm for adding binary numbers. That's not something I ever thought I would see in my life. I think I never even thought about the question, will I see a new algorithm for adding binary numbers? Kind of the answer was no, I already know the algorithm for binary numbers. But this one, it feels different. Of course, if you stare at it long enough, you can see, yes, it does the same thing. Of course it does the same thing. It has to give the same answer. So, okay, so how did I think about it? Now here I'll say the only connection to artificial intelligence, which I think is a very big topic that I don't think we know what to say about. But in general, what I try to make is machines that receive raw data and output understanding. So this seems almost impossible, just feeding just plain raw data and then producing understanding. But in fact, brains are machines that do exactly this. And if a brain can do this, then maybe we can make some other machines that can also do this. So I was thinking about how brains work, and the way I was led to this algorithm was by thinking about how brains process the information that's coming in. So when we look at a scene, so say we have say we look outside, there's maybe a tree, a house. I hope you forgive my not very nice artistic abilities, but right, we look outside, we see something. So our eyes process this information, and what do our eyes do? Well, our eyes have little, in the retina, there are cells that respond to small patches of the image. And in fact, if we go back into the primary visual cortex, we still see cells that respond to very small patches of the image. So if we zoom in on a very small patch of the image, let's say we zoom in on this, then we'll see something pretty simple. Especially if we don't have perfect eyesight, it'll be a little fuzzy. We'll see something very simple. So we can't have anything too complicated in the space. In fact, we could just make a list of all the possible things we might see there, right? We might see a vertical line. We could see lines at different angles. That's a very typical thing to find cells for. So all at this location. So right now what I'm drawing is a bunch of different, whoops. Is there's a bunch of different cells. There's a bunch of different, what should I say, little
Most
patches
of them
the
are
visual.
empty probably in your picture, but still.
Yes, yes. So empty would be a very common one. Yes. So all of these ones here are things that are different cells that are competing with each other to represent this little patch of image, this little patch of the image. And then if we move to a neighboring patch, say a patch just next door, we won't get a disjoint patch. We'll find cells that are responding to a patch that is overlapping with the first patch. And then at that position, again, we'll get all the same set of cells that are competing to represent that patch, and so on. So, for example, here we might see that let's say this unit is particularly active. Maybe I should put that in a slightly different color. And at the neighboring site, another unit is particularly active. And all of these activities together, they tell us what's in the picture. There's some consistency requirements, right? So if we have a horizontal, make another. So if we have two neighboring positions, let's say one for this region, one for this region, then if we have, say, this cell is active, representing a horizontal bar in the left-hand region, then the right-hand region can't really be empty. It has to be something like a horizontal bar. Maybe it could be a little different. Maybe it could be slightly tilted. There might be a curve passing through that region, but it needs to be compatible somehow. So we could draw, we can make a little matrix, a compatibility matrix showing what goes with what. So in this case, if I were to let me just straighten out that set of possibilities into a little column, right? So it could be empty, or it could be vertical, or slightly tilted, and so on. then if we consider those same possibilities in the next column, then there are some, we can look at which possibilities are compatible with which others. So of course they could both be empty, or like we had, empty can be next to a vertical bar, right? Horizontal can be next to horizontal or next to something that's close to horizontal. In fact, the lines that are at a similar angle are typically compatible because there could be a curve passing through that region. Okay, so without going too much into the geometric details, because this isn't really about geometry, I'm just trying to make the point that here, what we have here is like a compatibility matrix. We're saying which elements are compatible at one position. Having one receptive field is what the people who study these neurons call it. How those different possibilities, are compatible with the possibilities of the neighboring position. Okay, so that's all very nice, but it has too much of the real world for somebody like me. I want to deal with a very simple, simplistic abstraction. So let's consider a very simple world, right? So how did these neurons form, right? We had all these neurons. They formed by seeing what are the patterns that occur in the world, right? These are the patterns that are presented to the region that is feeding into these units as input. And these are the patterns that are typically seen. So the system learns to represent the patterns that are typically seen, that are typically visible. And of course, the world is right? Different parts of an image can occur at any position. So the things we can see at one position are pretty much the same set of things as what we can see at another position because of how the world works, because of the fact that our eyes move and there's a kind of translational invariance at the end of the day for the system looking at these things. Okay, so let's make a much simpler world. Let's make a world, say, consisting of zeros and ones. Let's make a one-dimensional world because that will keep our life much simpler. And let's make a world which, well, we want the world to have some structure because we would like our system to be able to learn to represent that structure. So let's say the structure is that the world never has two ones next to each other. So for that, I already made a mistake here. So let me just change one of those to be a 0. So that's the physics of the world. The physics of the world is we don't have two ones next to each other. We have, whenever we open our eyes, we see that the world looks like this, that there's some sequence of bits where all of the ones are isolated. Okay, but the way I'm describing it represents understanding the situation. Okay, but we want to have a system that just is exposed to the raw data and somehow on its own comes to this understanding. So what could the system do when exposed to this raw data? Well, like before we had units in the visual system that were responding to small patches of the real world, right? And they would represent all the possibilities that could appear in that small window of the real world. So let's consider possible windows of this one-dimensional world, right? We can pick some size of window, and we can have, right, overlapping windows. We'll have windows at every position, and this is inspired pretty directly from how our visual system works. And here I just picked an arbitrary size of 3 bits. It doesn't really matter. That would depend on, say, how much of the world a particular cell in your visual system is being affected by in this hypothetical one-dimensional world of bits. So what would we see? What would this, for example, in this window, what could we see? Well, over time, we see that there are various patterns of 3 bits that we can see. It could be empty, right? Or we could have a 1 at some position. Or we could
So we
have
have just strings without two ones near each other, and the graph
exactly, yes,
is what is
exactly.
compatible by shift one. Yeah.
Yes, yes. So if I did it right, then I think it would be these 5 possibilities is all that's possible for a window of size 3. If you do a bigger window, you'll get more. A smaller window, you get less. But here we get these 5 possibilities, and then the system can start seeing what's compatible with what at a neighboring position. So if we have this at one position, and then we have a neighboring position for the next window, which largely overlaps, then we can look at the compatibility matrix again. We can see, okay, what is compatible with what? Well, clearly the zeros are compatible. Oh, what happened here? Oh, I have the wrong, the zeros are compatible. And in general, it's compatible if the last 2 digits of the first triple match the first 2 digits of the next triple, right? So here, these are compatible. 1, 0, I guess both of these start with that. This ends with 0, 0, both of those start with that. 0, 1, just that. Is that correct?
No, there is first in the first column and second in the second. Yeah.
Like that?
Yeah.
Okay. Well, at least it's symmetric now, so there's some hope. I hope I didn't forget one. Okay, let's
Yeah, we should have 8, which is the next Fibonacci number, and I guess we have 8.
1, 2, 3, 4, 5, 6, 7, 8. Yes, we have 8. That's right. Yes. That's a nice way to double check. I like that. So yeah, so now let's draw this in a slightly different form where I'll draw a line traveling from left to right under each triple. And then have the same thing next door. And now I'll connect these with slightly smoother lines.
And then we're looking for trajectories from left to right in these things.
Well, as let me see. Let me just finish. Oops. This one should go to both of those. This one also comes down here, and this goes to those. Okay. So now the only advantage of this is that when if I draw it repeatedly, it fits up with itself a little more smoothly, and it's easier to talk about what kind of system we're making here. So put one here. So then I can put more and more. So we'd have a bunch of these representing the world with the, right? This is like the different parts of the visual system, each representing some local patch of the world, and neighboring parts of the visual system have to agree on what they're seeing. We aren't representing the world in terms of independent bits, like a digital camera would do. The brain doesn't work with independent bits. The brain works with bits that are not independent. And in fact, if you think about what brains are really bad at, it's independent bits. So in a whole page of complicated mathematics, what mistake are you most likely to have made? A sign error, flipping a bit, flipping one bit. Why? Because so much of the mathematics we do is basically unaffected by flipping the bit, so we don't notice that it was flipped. the problem is exactly that the bit was independent of everything else we were doing. If the bit wasn't independent and there was a lot of meaning with the sign, then we wouldn't make the mistake. But independent bits are what we're really bad at. It's the concept computers are built on. The foundation of a computer is the idea of an independent bit. If you can't store an independent bit, you can't even begin to make a computer. And yet we are pretty bad with independent bits. Anyway, let's consider this diagram for a minute. So here, with it drawn like this, we can consider paths through the diagram, right? So any path through the diagram is a valid world state that we might see. It's valid according to our visual system. If the actual world had some physical property, maybe bit number 2 and bit number 21 are always the same, this visual system has no way to notice that. So this visual system, because it was based on units of a window size of 3, it can only notice phenomena up to that scale. Okay, but it should notice any phenomenon up to that size, and for those rules of regularity that it has noticed, that is the regularities that occur up to that window size, then every world state that is valid is representable in this visual system, right? If it would see all zeros, that would be this one. If it would see, right, every possible path we can see through this diagram is a possible state of the world. And the visual system, so with this representation, the visual system can learn to represent this huge number of possible strings. So here I wrote 4 columns, but we could imagine that there are 100 columns or 1,000 columns, right? We have megapixel cameras that are 1,000 pixels wide. We don't think there's anything strange about that. If you imagine 1,000 columns here, there's a huge number of possible bit strings. There's no way we would ever have time to learn them all. But since we were using little windows, within each window, we just had to see, okay, these 5 patterns occur, and the other 3 bit strings that aren't appearing, those never occur, and this doesn't take very long to learn, and it can be learned simultaneously at every position. So, okay, so this representation is showing, it expresses in some sense all the possible worlds that could exist. Now we would like to simplify this representation. Yes? We would like to somehow automatically shrink. We're still in a form which is completely formed by the raw data. We see, so when I was describing how to draw these connections, I was talking about the overlap in these bits. But the visual system doesn't need to think about overlap in the bits. The visual system just notices, oh, when this unit for 3 zeros is active, sometimes this unit, which we know is for 0, 0, 1, sometimes this unit is active. So since sometimes these units are active together, those are compatible with each other. But it's never the case that this unit is active when this unit is active, so those don't have a line between each other. So these lines between the columns are also very easily learnable. And the learning only takes an amount of time that's determined by the window size, not by the overall system size. Okay, so we get this format where we can represent any possible world state with this type of description, and we would like to simplify it. So let's talk about diagrams that look like this for a minute. So I call these zipper diagrams because here we see a zipper, here's a zipper, here's a zipper, and so on, right? It looks like a zipper, so I call it a zipper. Also, because if we want to play with the diagram, we can, well, let's see. Yeah. We can do operations like zipping the zipper back and forth, right? So we could move a zipper to one side or back to the other side, and it won't it won't affect the diagram. What does that mean when I say it won't affect the diagram? What it means is this diagram represents all possible worlds, right? This was the bit string of all zeros. When we open our eyes and we see all zeros from the far left to the far right, it's all zeros. Here we opened our eyes, we saw 1, 0, 0, 1, 0, 0, and so that was represented here. Every possible world is represented by some path through this diagram, and different bit strings have different paths through the diagram, and if you have two strings that lead to the same path through the diagram have to be the same string. There's a one-to-one correspondence between paths through this diagram and bit strings. And this is independent of the window size, right? So here we did windows of size 3. And if we count the total number of paths through the diagram, we'll get some nice large Fibonacci number, right? So I won't spend my time counting all the different paths through this diagram, but there's some number of different paths, which is given just by the fact that this diagram is representing bit strings of what? Size 3, 4, 5, 6. Bit strings of length 6 are represented by this diagram here.
No, it's all clear. What is not really clear is what you claim about this moving of a zipper. You speak about some transformation of this diagram that does not change the set of paths, or what?
Yes, exactly. So that's what I mean about the it's okay to move the zipper back and forth. It's not going to change the number of solutions. Let's say that these possible paths through the diagram, they're solutions. I'll just call them solutions as a word for it. It's a solution to this set of constraints. So this is a constraint that we have to be on one of these. We have to choose one of these 5 options, right? And we have a constraint here and so on. And to satisfy all the constraints, there are, right, these compatibilities show that these are the possible solutions, right? So the overall number of solutions here for 6 columns is it's a large number. It's going to be exponential in the number of columns, but it will be unchanged if we move a zipper back and forth. This is a trivial zipper operation, not very interesting. Let's consider.
Can you apply some this zipper operation to our diagram just to see what do you mean exactly?
Yes, I will in a second. First, because there are only 3 zipper operations, I'll show you the 3 zipper operations, and then I will start doing it to the diagram. So if 2 zippers are facing in the same direction like this, then it doesn't matter which one of them comes before the other. They can pass each other. They can move back and forth. If they're facing in the same direction, they can just slide past each other. There's no difference between these. If we think about the meaning of the zippers, right? The zippers are representing that there are 3 different options over here, and by the time we get here, they've merged to 1, and here's the same. So this operation isn't going to change the number of solutions. And then the final operation is the more complicated one. So that's if the zippers are not facing the same direction. So here, if the zippers are not facing the same direction, then as we move this zipper this way, it's unzipping everything. And the same thing, this zipper moving this way unzips everything. And when they pass through each other, they unzip each other. And so then we get to each zipper gets unzipped into 2 zippers. So the one from the right here, as it was going this way, it got unzipped by this zipper into these 2 branches. So now it's going to appear in both places. And the same thing on the other side. Okay, so this one, it's a little bit hard to picture the 2 zippers unzipping each other, but there are some ways to think about it. You can think of, in this diagram, here we have the part where it's unzipped here has access to one piece of information, and the part where it's unzipped here has access to another piece of information. As we're unzipping, we're informing more and more of the diagram about this bit of information. And the same thing going the other way. And so here in this region, where the two zippers have passed each other, actually this region is aware of both bits of information. And we can see that the 4 possibilities correspond to the 4 possible pairs of bits that we originally had. Or you can think of it like you could imagine that in quantum mechanics you did some experiment where, so let's say you do some experiment in 2 spatially different places, and one of them, say, splits the world into the 2 possible answers for, I don't know, whether you had spin up or spin down on an electron over here, and that information is traveling along. And then somewhere else, a similar experiment was done, and the world is splitting into 2 possible worlds for that. Then as those pieces of information approach each other, it looks like this. And as those wave fronts pass each other, then after they pass each other, then in between we have the 4 possible worlds that are aware of both possible outcomes. Now, whether you think that's a natural way of thinking about it, probably thinks of whether you were, I don't know, if you spent your time in the past thinking about this type of information splitting the world apart. Here the information is just splitting one zipper.
About what you say is that the total number of the total connections between left part and the right part remain the same after the transformations. But if we have some structure which corresponds to internal bits, I guess the structure is now lost. So if we take a vertical section, it doesn't correspond to any factor.
Yes, the vertical section here doesn't know either of the bits. The vertical section here knows both of the bits. And over here, we just know one of the bits. The same one we do here. And the same thing here. Yes. Yeah, so yes, thinking about it as the region that knows about the bit is a pretty correct way to think about it, because that's really what it's that's pretty close to what it's representing here. Okay, now this. So I'm done. These are the only zipper operations. I'm done showing the zipper operations. And this is the only one that offers any hope for simplifying the diagram. So let's see if we can simplify the diagram with that. Get rid of those. Okay, so now we will look and see if we can find some instances of this pattern here. If we can find them, then by applying this transformation and going to the simpler form, maybe we can simplify this diagram. Okay, so let's see. So here's an example. Right, this is one example of this pattern, right? We're looking for 4 zippers that face each other, and they face each other in the way where each zipper is facing both of the other zippers. We have 2 zippers facing 2 other zippers, and each one faces both of the other zippers. Right, so it's right, we have this kind of quadrilateral arrangement, and so over here we can see that we have one of those, and of course we have that in each. We have the same thing in each block. So let's see if we can simplify that. So how would we simplify it? Well, the answer is these 2 come together, and these 2 come together, and then those are joined. So that's the simplified form. And we can do that at each position here.
But do you have some specific measure of simplicity in mind, or just you do some transformation?
So there are fewer zippers, there are fewer lines. So of these operations, these operations don't really affect the simplicity. They look pretty much the same on both sides. Or maybe this one simplifies it a little bit, because there's more of a region where it's just 1 wire instead of 2 wires. But on this side, probably any simple measure of simplicity would probably say this one is simpler. It has 2 zippers instead of 4 zippers, and it has 1 wire instead of 4. So if we're doing some simple measure of simplicity where we just count things, then this is definitely simpler. Okay, and I'll just say ahead of time, you would hope that in general diagrams like this would have a canonical form, but no, that's not true. It's not the case. You can easily make a diagram where you can apply this operation once, but then you're stuck, you can't do it again. But the ways you could apply it once, there are different ways you could apply it the first time, so you don't get a canonical form. So for trying to simplify things, yeah, we might, eventually we'll get stuck because we can't simplify everything to nothing. And where we get stuck could depend on the choices we make. But right now I'm not going to worry about that too much. I'll just try to simplify it and see what happens. So let's look for another place we could simplify. Let's see. So here, this is splitting into 2. And then those do face 2 different zippers. And those 2 different zippers actually do face the same other zipper. So this is an instance that can be zipped together. So if we do that, what will the result be? I'll copy the diagram. So we get the diagram. Now what happens if I'll leave the previous one showing. Okay, so let's try to simplify these 4 wires down to a single wire. So we want to put this zipper, also this zipper we want to move forward. Okay, so we'll have to look at this diagram to remember what we're doing. But what happened now?
But you erase something which is not in the changed part also.
Did I?
In the third column, you have 0, 0, 0, and 0, 0, 1 connected to one thing to the left.
Oh, you're right.
It was not a part of what you did.
Yes, that was a mistake. Thank you. Good. Okay, yes, because these are the 2 lines on this side that we want to connect. And these are the 2 lines on this side. So I'll go ahead and connect them because that's the reduced form. And then these 4 zippers have zipped themselves up into just 2 zippers, and now they've passed through each other. Okay, and if we do that, we can also do that. Well, let's look. So now we took a bunch of labeled lines, and I have a bunch of floating labels. So what's going on? We had 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. These are all the triples that have a 0 in the middle. So I'll relabel that line. I'll just put dot, 0, dot to indicate that there's a 0 in the middle of the triple and the other positions are unconstrained. Okay. And then we can do the same thing. We can do the same thing again, right? We still have this pair of zippers facing this pair of zippers. So we can do the same thing there. And that will do the same merging here of the 4 cases with a 0 in the middle. Those 4 wires will get merged into a single wire. And we can do that at each position. So if we do that at each position, we can make a diagram like this. And then what are the connections? Well, the 0, 1, 0 connects only to this new condensed wire. Okay, so 0, 0, 1, 0 connects only to that on the right-hand side. On the left-hand side, the 0, 1, 0 also only connects to this condensed wire. And this condensed wire, what does it connect to? It connects to the next door neighbor condensed wire, as well as the connection we already just drew. So it connects over here. And that's it. On the left-hand side, it also only connects to the the condensed wire of these four. It connects either to the condensed wire on the left or to the 0, 1, 0 on the left. So this here we see all the connections, right? Everything connects except for 0, 1, 0. And now we can't do any more compression of the circuit. We've gotten stuck. And so what have we achieved?
It's not very clear what. So initially, your previous diagram showed some binary relation between the left column and the right column.
Yes.
And now you combine some strings on the left on the right
yes.
into one group. So what you then claim about the path in these two diagrams? You say that they are in one-to-one correspondence, or what?
Yes, they are in one-to-one correspondence. So any path we pick in the upper diagram, let's say we pick a path like this. Well, that's not a very good example. First of all, let's use the full diagram that has, right? So if we pick some path like this, so this corresponds in the collapse diagram. I'll just make a little annotation. So to make the collapse diagram, we collapse these four values. We collapse these four wires into one wire, and we did that at every position. Okay, so what did this blue path do? Let's try to draw the blue path on the new diagram. We started at the collapsed one, we went again to the collapsed one, then we went to the 0, 1, 0 line, and then again to the collapsed one. Okay, so I claim that slightly counterintuitively, it looks like there are many more paths through this diagram than through this diagram, but I claim there are exactly the same number of paths through this diagram as through this diagram. They're in one-to-one correspondence. And this is because with the operations we were doing, with the zipper operations, each step we did preserved this one-to-one correspondence. And so in this diagram, it looks much simpler to us. It looks like there are many fewer options, but as you're traveling through the diagram, there are just as many chances to split. So here we had a chance to split entering the second column. Here we have a chance to split.
I am lost. So look at your blue path in the bottom diagram.
Yes.
It seems that it corresponds to 4 paths in the original one, which starts with 1, 0, 0 and 0, 0, 0 and.
Yes, and this is the same thing that was not going right with the example I was just starting to create, with what I was just starting to say. So these problems that this lack of correspondence is because we didn't extend the picture more to the side. So here, what I should have done is I should have included even a little more. I should have included one more column on the left. Oops, not that.
So you say that if we continue this diagram infinitely in both directions, then we have one-to-one correspondence between the paths.
Yes.
Yeah. Okay.
Yes, I should have. And now I think I think even at this point, we should have a one-to-one correspondence here if I just extend it one more column.
If you
to
extend
the
only one, we have the same problem on the next level. We can have first one and last one, or zero.
Yeah.
So it's
yes. So from this,
they are distinguished only on the next layer.
Yes. So the problem is I cheated in a way because I zipped together these 4 lines when in fact there were no zippers over here. But when I collapsed them to one I was doing the operation as if there had been these zippers over here. And if we would imagine that that we would see the zippers over there, then then we would have been able to do this operation. So I cheated by assuming there were more columns, because in my head there are lots and lots of columns.
Okay, I guess that for the infinite picture, the correspondence is more or less clear. It needs to be checked, but probably it should work.
Yes, and so at this point, we've reached a local minimum. We've reached a state where we can't collapse it any further. And in fact, for this example, you will always wind up with this picture here. And if we notice that 0, 1, 0 is the only triple that has a 1 in the middle, we can see that in each column here, what we're detecting is just the bit of the central column. And all of our collapsing has been merging bits of the non-central column. That just happens to be the case for the operations we did, because, well, we basically did one merging operation, and this merging operation merged the 4 cases that had a 0 in the center column, and and the other wire is the 1 case that has a 1 in the center column. So we can think of the 2 values here as just being 0 and 1. And we can see that the diagram is showing very clearly the physics of the world, which is that you cannot have 2 1s after each other, but any other combination, any other sequence is okay. So any sequence of bits is okay, but if you just had a 1, you have to go back to 0 before having another 1. You cannot have 2 1s in a row. So this is nice in a way, because we had a system that does some local learning, that doesn't know anything about how the world works. It just has some limited windows with which it looks at the world. It just collects the statistics, not even complicated statistics in this case. It's just, what does it see? Well, these are the 5 things it ever sees. So this window develops 5 units to represent those 5 things. The neighboring unit develops 5 units representing the 5 things that are seen in that window, and so on. And then these units connect to each other based just on which ones can appear simultaneously. That tells us what's compatible with what. So all of this is completely coming from our experience with the data. We could have started with windows of size 5, and then we would have a much longer set of possibilities of sequences of 5 bits. We would have a much larger diagram here with many more wires, many more zippers, but it would have exactly the same number of paths through the diagram per column in the long run, right? So the slight caveat is, even with the first column, we've specified 3 different bits. So even with just 1 column, there are 5 paths through this diagram. And if we would be looking at a window of size 5, then there would be, 13 possibilities. And so we would see there are 13 possible paths through 1 column of size 5. But if we consider 3 columns, right? If we consider a diagram of this size that's also covering 5 columns, then we would see there are 13 paths through this diagram, and those correspond to the 13 possibilities in the larger diagram. And in fact, we can get the larger diagram just by unzipping these zippers through each other. So doing this operation, but in the direction that makes more zippers, we can get the other diagram, because these zippers are exactly, these two zippers, for example, are exactly removing the fact that we're losing the information of what was the left-hand bit in this triple. So as we move the window over, we lose that information because all we're remembering are these two zeros. And so those two get zipped together into the cases that are using those two zeros. So the zipper represents the loss of knowing about this bit. This bit is no longer distinguished in the possibilities. But if we would unzip, if we would move the zipper this way, we could get this column to also know about this bit. And if we do that with all the zippers that are facing that direction, then this column would know about a window of size 4. So we would get these 3 zippers would unzip through this column, and we would get 3 more lines. We would have all 8 possibilities in this column, and so on. So what we've done is we have a system where we simply fed in the data and we turned the crank. We didn't apply any intelligence to what we were doing. First we just observed what patterns do we see locally, and then we applied this simplification rule. Also, we just applied it wherever we saw it. We didn't try to do anything intelligent. And what we came out with was a pretty clear representation of the physics of the world, where the complexity of this diagram matches the complexity of the physics of the world, right? This diagram is just complicated enough to capture the idea that you cannot have 2 ones after each other. This is very similar to simplifying a finite state machine or finite state automaton, right? In that case, this would be a time dimension, and the process is it's similar in spirit. So yeah, the possibility of being able to simplify, in that case, there's a unique simplified version, and by the nature of the problem, it's forced that the same thing has to be happening in every column. Here, it just happens to be the case that we're considering a world that is translationally invariant. If there were a particular direction where a bit is always 0, this model would capture that. Okay. So
yeah, but in case of finite automata, there is kind of unique minimal automata, and you say that now it's not the case.
Yes, now it's not the case. We can make a, let's see, I should be able to make some simple counterexample. Let's see.
No, just to clarify what you are claiming and what you are not claiming.
Yes. I think if we have a picture like this, we get something with 2 minima, because we could use these zippers to compress. Or because of the rule that we can slide zippers past each other without affecting anything, we could alternatively use these zippers. It's not a very clear color. These zippers to compress. And once you've done one of those compressions, you can no longer do the other one, because you messed up the. If you move the red zippers, then you messed up the light blue zippers, and vice versa. So you can only do one step of simplification here. So that's an example that shows it's not, you don't get a unique result. So to come back to the addition problem, so where did the addition algorithm come from? Right here. So yes, here in the simplified case with the no 2 ones in a row, we knew what the rule was because we designed the world ourselves. We knew what was happening the whole time, and we were just testing out the methods and seeing how the methods work. Now with the addition system, first of all, we have to see, well, what is the world? The world is that every time we open our eyes, we see an infinite sequence of bits, or maybe it's finite, but we see a lot of bits. And it's always 3 rows of bits that are part of a valid addition problem. I should say, I don't know. I'm not very good at making random addition problems.
Okay, we can imagine this.
Yes. So every time you open your eyes, you see that. And then
so you probably want to say that we look at, now we have a column as a symbol, and we have a window of size 3, and then you somehow apply the reduction process and get something like carry bit.
Exactly. Yes. Yeah. So if we look at a column, so I never really thought about addition problems that much. Maybe it's obvious to everyone. So I was thinking about, oh, columns of size 1. So actually there's no structure, so there's no constraint among those 3 bits. All eight possibilities are possible in an addition problem. And if you pick a larger window, like here's a larger window, so I don't know how much structure there is, but I'm sure a window of size 3 is big enough. But there are quite a lot of possibilities of these. You get, I don't know, 32, 64, some large number of possibilities. But you can start zipping things up, and eventually you get to a point which is basically representing these 8 possibilities, which is, let's see, if we have for example, a wire for 1, 1, 0, 1, 1, 1. So I'm putting them in a slightly strange order, but oops. So this should be all 8 possibilities. Okay, and then let me make another neighboring column that's just the same. Okay, so what happens between these columns? Well, these I messed up my thinking slightly. Let me just rearrange these for a second. Okay, let's try this. This pattern, but now I see I made a mistake. I have 0, 1, 0 twice. I should have 0, 1, 1 because it was also down here. So I think that should be all 8 possibilities.
No, probably we cannot also follow and check all this. Maybe you can just say informally what you want to see here, and we will believe you.
So actually, what you see here is simple enough. I just want to draw it because then it will be easiest to explain by pointing. So these merge. Yes. So I won't go through some long operation of collapsing lots of zippers. I'll just say that after you do that, you get something like this, where yeah. We have
there is an informal idea that if we have 0 and 1 in some column in the summons, then this column acts as a carry bit transmission, and if we have 2 zeros, its carry bit is consumed, and if we have 2 ones, the carry bit is produced.
Yes. So
maybe that's what you want to.
Yeah. So following with that, so that provides actually a nice way to simplify it, because what we find is, yes, we have these 8 possibilities in that column, but between 2 columns, in fact, we can reduce the possible amount of information to just 2 possibilities, which correspond to the carry bit being 0 or 1. So this is a very familiar This is a very familiar piece of information, and we can see that that's the only connection between neighboring columns, which we're kind of familiar with from the traditional algorithm, that there's a carry bit which is needed to be transmitted to the neighboring column, and which depends on, it has some relationship to the previous column, it has some relationship to the next column, but that's all that we need to keep track of. And yeah, and then I think I should just rearrange those also. And then we see that the items that are connected to the one carry bit and the items connected to the other carry bit are not too hard to figure out. So what has a carry of 0? This one, right, this has a carry of 0. This has a carry of 0. And these both have a carry of 0. And these all of these cases have a carry bit of 1. Right? This case looks a little funny, but if this is what you see, that means that the previous step also had a carry bit of 1. That's the only way you can get this triple. In fact, yeah. So these are the 4 cases with the carry bit of 1, and then we can just look on the left and see which cases are the carry bit of 0. It's right here 1 plus 0 is 1, that's correct, doesn't need a carry, but 0 plus 1 is 1. 0 plus 0 is not 1, so that can only have happened if there was a carry bit. But this one is correct with no carry. This is correct with no carry. This one requires a carry, requires a carry, requires a carry. So the carry bit is connected to 4 things on each side, but not the same set of 4 things. And at this point, we can zip things together a little bit more. We can, right, we can pull, well, we can, well, I should probably just provide the diagram that we get at the end. So at the end, what we get is that well, we'll still have those carry bits. Let's see. So at the end, what we get is that we can put these together, we can, we have at this stage, we have, so there's a carry bit which is connected to the upper ones on this, these upper ones on this side and these on this side. What we get is a diagram where we can separate, where we get one line. So just like in the previous example, we were able to collapse to a stage where we had to ignore some of the bits we were writing there. In this case, we get a wire where what we know about the wire is that of the 3 positions, the upper 2 are equal. And then it splits in, then it, yeah. Then this one splits into, and this, we've also, oh, I'm being slightly incoherent. So this is a merged wire of 4 possible wires. Which wires? It's the 4 central wires. So the 4 central wires get merged to this form. So I should probably just put that in a, well, I'll erase these 4 central ones. And then we have this on each side. And then, oops. And then these also merge. So we get these little little bubbles of local information which doesn't matter anywhere else for these cases where the top 2 bits were different. And as we know from an addition problem, if the top 2 bits are different, it just doesn't matter whether it's 1 on the top and 0 underneath, or 0 on the top and 1 underneath. So that information is of no interest to the neighboring columns. So that information is just a local little bubble, and nothing beyond that cares about it. And then here in between, we have the 2 possible carry values. And in between, we have this happening. And so this, if we look at what's going on, we can see that this is the pattern of the 4 zippers having zipped themselves up into 2 zippers, and the same thing here. And so the 4 wires, the 4 different possibilities where the upper 2 bits were equal have been compressed into 1. And when we unzip them, it has to happen in a certain way if we're paying attention to the labels on the wires. And the way that is that the upper bits determine which direction we're going in, right? And this makes sense. If the upper 2 bits were 0, there's definitely no carry, right? So if the upper 2 bits were 0, we know there's no carry. If the upper 2 bits were 1, we know there is a carry. And the bottom can be anything. That doesn't affect the carry. And on the other side, it's slightly different. It's the bit on the bottom, which is related to the carry, right? If the upper 2 bits were 0, then the bit on the bottom depends on the carry. Then the bit on the bottom is 0. If the upper 2 bits, if the bit on the bottom was 1, if the upper 2 bits were 1, the bottom still depends on the carry. So the upper 2 bits, since the upper 2 bits are the same, they don't affect the sum at this position. The lower bit is just a reflection of the carry, regardless of what the upper bits were. So probably what I was saying was completely incomprehensible, and in the meantime you were thinking of your own way of thinking about it, which is good. And so what I hope you have concluded is that this annotation I made in red is correct. The carry tells you what the bottom bit will be in the case that the upper 2 bits are equal, and the carry tells you what the top 2 bits were in the case that they were equal. But something, yeah, should be, and in these other cases, we have cases that where if either there was no carry coming in and no carry going out, if the top 2 bits are unequal, or there was a carry coming in and a carry going out.
So what you want to say that the columns which have 0 and 1, or 1 and 0, they act as carry propagation, and so this corresponds to the why you copy to the next dot.
Yes, yes. So if we make copies of many columns like this, and we look at some path through it, then what we see, we can see. So if we look at that blue line, it will spend some time at the top, then it will spend some time at the bottom, some time at the top of the diagram. Where what I mean, the top of the diagram, I mean this part, and the bottom of the diagram, I mean this part, and this part in the middle is a chance for it to change. And so these regions are the regions where the top 2 bits are different. And those are the regions where the carry doesn't affect the answer, but the carry just propagates across that region. And then occasionally there are columns where the top 2 bits are equal to each other. And at those positions, the carry bit drops out into the third row, and the new carry bit is picked up, if we keep moving to the left, from the upper row, from the top 2. Well, the top 2 columns are the same, and that's the bit that determines the new carry. So that's what the algorithm is doing. The algorithm is just trying to reflect this idea that the only time there's really information of interest being transmitted between different places is when we're at places where the top 2 bits are equal. That's where the carries are initiated, and then the carries don't affect anything that's happening until we get to the next place where the top 2 bits are equal, and then they land at the position in the bottom. And so that was the copy phase, where we would take the bit from one position with a dot. The dots were the positions where the top 2 bits were equal. We would take that bit, we would look for the next column, we would go across all this path and then look for the next column where the top 2 bits were equal, and that's where the carry has its effect. And so in that copy phase, where we were just copying bits, we were processing all of the carries. And then in the fill phase, we were dealing with these regions where the top 2 bits are not equal, and those regions just the same thing is happening the whole time. The regions that have the carry equals 1, and in those regions, the third line is 0. In the regions where the carry is 0, the third line equals 1. So we fill in with the opposite of the bit that we saw. So the path towards the algorithm is not super simple, perhaps, but most of it was obtained just by turning the crank. So we didn't have to use. So the algorithm came just by using the simplification rules, trying to see at the end, what did we get? And I hope I haven't made a mistake here, but maybe there's some, I don't know if there's some, I hope this diagram is correct, but I didn't produce it at this moment through doing the zipper operations. This diagram is clearly correct, and then there's just, I think, yeah, there's just one zipper operation we need to do to get to the next diagram, which is, right, the one that connects, yeah, we separate out a couple of the zippers from here to reduce these 4 lines into 1. So we're using this zipper, right? We're collapsing these 4 lines. So we're using this zipper and this zipper. So we apply that zipper transformation rule once on this diagram, and it yields this diagram. And then just looking at this diagram and what the solutions look like, that's what led to the new addition algorithm. So this makes me very happy, because we had a system where we just feed in exposure to raw data. Then we apply a mechanical simplification operation, and we want some kind of understanding to come out. And some kind of understanding did come out. So I see addition problems very differently now than how I used to. So I also find it interesting that because there's no unique normal form for having a zipped up system, to me, this makes a lot of sense. Together, it makes a lot of sense with the idea that different people have different ways of understanding things. And these ways don't map onto each other perfectly at the low level, even though they might both be perfectly valid ways of understanding the system. So in this case, there are other ways we could have done this final zipping together. We didn't have to pick these 2 zippers and these 2 zippers. There are other choices we could make. I chose these because it's the most symmetric solution. Other choices are somewhat less beautiful, you could say. So this is the most symmetric way to zip everything up. But there there are only, I don't know, maybe 9 different ways to zip things up. And so there are 9 different diagrams, many of which are maybe a reflection of another diagram. There's symmetries among them, so they aren't that different from each other. And they would each, by considering each of them, you might be led to a slightly different type of addition algorithm, right? So there are many different ways to understand binary addition, all of which are equally valid. And then, but they're all expressing the same thing. And then if we expand that understanding to be a little more complicated, so if you get someone who's really familiar with binary addition, then they might have more than this simplistic diagram. They might have a more complicated diagram like this, because they're familiar with even larger windows and thinking of all the possibilities. And then maybe, and they can relate to all of the more simplified algorithms. So at least for me, feeding in the raw data, turning the crank did yield a new understanding for something where I did not expect any kind of new understanding. In fact, before that, I hadn't even realized that addition was symmetric in zeros and ones, although I should have been aware of this. So for example, having a different algorithm, you might immediately think, oh, what would the electrical circuit for this be? If we use digital logic gates, do we get a different kind of circuit? And what's interesting is, no, you get exactly the same circuit you always get. It's just you aren't thinking of, right? You get the full adder circuit, and in a full adder, you have 3 bits as input, right? The first summand, the second summand, and the carry bit, and then the outputs are the majority gate for the carry bit, and the XOR gate for the bit at that position. So in fact, by looking at the circuit, I should have realized years ago that addition is completely symmetric in 0 and 1, because those 2 gates are completely symmetric in 0 and 1. And now looking at what would be the digital circuit for this new algorithm, it's just a different way of thinking about the circuit. It's a different way of thinking about the information flow, but you get exactly the same circuit. You just have a different way of thinking. You aren't thinking about it so much in terms of the carry bit as in terms of this the bit that's being copied a long distance, and the bit that's being filled in between those gaps. So that's where this algorithm for adding binary numbers came from. I hope you like the algorithm. If you try it, I think you'll find it's easier and faster. Even though it has 3 passes, the passes are so trivial that you don't even have to pay very much attention while you're doing it, and it's very easy and quick to do. And there's no step as complicated as adding two bits. All the steps are simpler. You put dots where the numbers are equal. You copy bits to the neighboring dotted column, to the next dotted column, and then you fill in the gaps with the opposite bit. So the operations are very simple. So that was basically what I planned to say, to give the algorithm and how the algorithm arose from trying to think about how brains work. And I was surprised that anything interesting actually came out of this exercise. So for me, it was very interesting to see that, yes, what feels to me like a very different addition algorithm came out of this.
Did you try the same analysis for other cases, like, I don't know, ternary addition, the first simplest idea?
We could.
If you have base 3 instead of base 2, you will get.
Yes. So with higher bases, you're forced to have more of the addition table built into what's happening in every position. Because except for the carries, you really are implementing addition just among those 3 digits that you see in one column.
No,
so you aren't led to as nice of an algorithm. So this is the sort of algorithm that's particularly nice in base 2. Many of the algorithms are particularly nice in base 2. Like the square root algorithm is extremely simple in base 2. and so on. In the division algorithm, whereas in base 10, you have to kind of see, well, which multiple up to 9 times the number would fit into something. In base 2, it's up to 1 times the number. So you're just comparing if which of two numbers is larger. So,
no,
yeah.
but I guess there are still just 2 possible values of carry bit. So we just have more alternatives inside one bubble, so to say.
Yes.
So can you see, do you have any kind of idea of what or way to try to formalize or generalize this kind of local simplification or operation, which is your zipping, unzipping operation, so that it tells a little more about how we are trying to come to understanding with more complex pictures.
So these zipping operations will work. So for the type of situations I was describing, these zipping operations are sufficient for any initial window size you start with. Starting with a larger window size or more complicated system means you start with a more complicated diagram, but the end result will be the same. The end result will depend just on the physics or the constraints of the real world. But where it really breaks down, unfortunately, is that it is not easily extendable to 2 dimensions. So in fact, although I was picking 1-dimensional worlds just to keep everything simple, it turned out that this was not an easy thing to get rid of later, to say, oh, well, doing it in 2 dimensions is just the same. In 2 dimensions, it doesn't. You run into a problem that these zipper diagrams will have loops in them. That your 2-dimensional windows, will be connected in loops, where a loop has the problem that if you go around the loop, then you come back to a piece of information that you previously saw. So for example, a bit that you see at a certain position is represented, for example, the bit that you see at this position is represented in all 3 of these windows. But if we go to windows further away, that bit is not represented. So these bits, wires which differ only in bits that appear in this column, will get zipped together as we leave these windows and go to some other region. But then if we come back to this region, this information will be unzipped again. But if we have a 2-dimensional picture, we can leave the region where that bit is represented and then come back to that region along another path. So if we unzip the system with the zippers here to represent the bits in that column, then we can keep unzipping. And when we get back to that region, the zippers don't realize that's the same bit they already saw. So then they will unzip the same information to represent all 4 possibilities of what these 2 bits are, because they think the 2 bits are different. But in reality, there are only 2 possibilities. And so since the zippers aren't able to realize that the information is the same, then the method breaks down. This is exactly the same problem that the belief propagation in factor graphs has, or in belief networks, where the network has to be a tree. And if the network is not a tree, then the message passing gets really messed up, because that's also a case where if it's not a tree, you can go around in a cycle, and then when you go around in a cycle, you don't know if the information is your own information or some new information. And that's exactly the same problem. In fact, you can draw belief networks. So if in all the pictures I was drawing, these compatibility lines either existed or didn't exist, and these wires existed or didn't exist. But if we imagine each of them existing with some probability, existing to some degree between 0% and 100% present, then we get exactly the same formalization as belief nets and factor graphs from graphical models.
Mm-hmm.
But
I don't know if that
there is
answers
some
the
kind
question.
of question even for one-dimensional things. So imagine we start with some what is called suffix shift, something. We have finite automaton with several states and consider all the trajectories. And then we forget about this automaton and look only on the trajectories and trying to apply your algorithm. And then
Yes.
success means, for example, let's define it, for example, just that success means that we get some another automaton which has the same number of states or close number of states or something like this. And there could be some theoretical or experimental result showing that more or less in most cases, in all cases, this analysis is enough to come close to original automata. Is there something like this known?
Yeah. So I don't think something like this is known, but my guess of what would happen, and now that you say the question so clearly, I should double check when I have a few minutes, I can double check the answer. But my guess is that we would be able to show that for this case of the finite automaton processing its input, we could prove that there's a unique compressed form of zipping up the zippers, and that this unique form should correspond to the minimized form of the automaton. But I would have to think more about what exactly the correspondence is and what we want to, what exactly the lines would represent. So in the examples I was giving, we could say the operations preserve the number of solutions, which is which ways we take lines through the device. But actually, no, this seems the same as as for the finite automaton. It seems the same because there the number of solutions means the number of ways that you could start in some state and then receive some sequence of input. So that number should be the same regardless of how the diagram is drawn. So I think this method should be equivalent to the minimization algorithm of the automaton, except that this method is very wastefully doing that minimization almost independently at every time step.
Yeah, but for example, what I don't really see. So imagine we have some kind of non-local dependence. For example, we want to consider all strings of A, B, and C. When if we have A somewhere, we never have B somewhere. So it doesn't appear on any finite level somehow.
Yes. So then the method I described will not learn this from just observing examples because in the way I described it, it depends on having a finite window size or a bounded.
Yeah, probably we will lose something, but it's interesting what we can still get.
But we could still draw the diagram. We could instead of doing exactly the same procedure where we look at lots of examples and have it learn the system, we could draw the zipper diagram by hand, showing the states of the automaton, the possible transitions, and the new state. And then we could take that structure. Maybe it should be extended. I don't know if that maybe that helps the zipper operations. I'm not really sure. Maybe it doesn't help. But then that structure should be collapsible into a smaller structure which has fewer states, but still processes the state-to-state transitions in what is effectively the same way.
Okay, so what I'm saying that it would be interesting to have some kind of theoretical or experimental claims which somehow show that this nice construction is somehow maybe not maximally powerful, but close to some, in some sense, close to whatever can be done and so on.
Yes. So I think it should be provable that it does the same reduction as the standard reduction of states.
Well, maybe not provable, but I guess maybe there is just kind of understanding what is the analytic power of this approach. Maybe there's some kind of combinatorial explosion which happens if we have, I don't know, automata with 15 states and give the examples and then show this machine show this set of examples, and then it tries to do something. Is it really hope? Is it?
So so that's the question. Is there would there be some way to learn from examples in a way that can learn some kind of non-local relationship?
No, non-local or even local relationship, but no, between you have maybe you have so many possibilities to make this equivalent transformations. So the machine will be very lost quickly in these possibilities, or just how it will practically work. You know, there is one example and it works perfectly, but how far can we go beyond this?
So we can think of this diagram as being a machine with 5 states that processes binary input, and from these 5 states, when we receive a new digit, then these transitions are taken. We could label all of these transitions with a 0 or 1 for the bit of input, and then we're again led to one of these 5 states, and after the reduction we have the simplified form where we have just 2 states, and it accepts exactly the same language, right? So I think a very tight, a very close formal relationship can be developed there, and yes, and now that you ask these questions, clearly it makes me think I should do that.
Or someone.
I should find this correspondent. Yes.
No, maybe one whom I see on the screen can doing something. Just kidding. Sorry.
Yes. Yes, it would be very nice to show that this connection, and it might also be true in the maybe the connection would provide something in the reverse direction also, that in fact this method does not do anything more powerful than the state compression of finite state machines. That might also be possible. I don't know. But that would be very interesting to me, because it's not so far I only thought about this method as being kind of a compression of representing structure in the world, of a way of working towards having a world model of the world that you see when you open your eyes, right? So this is going back to the AI perspective of we would like a system that after it sees lots of input, then it develops its own world model. And so that's how I've usually been thinking of this. And I don't usually think about the correspondence with one of these directions becoming time, but I think it makes sense to I think your questions are very good ones, and they make me want to answer them.
Okay. No, maybe we can have a reserved place for your talk, not the next week, but some point. Also, I just there is a fantastic example of analyzing a non-structured data made by humans. So there is an experiment. People started looking at local rules with this to try to find the minimal periodic two-dimensional cellular tile set.
Yeah.
And they did a very thing which I believed would be completely impossible. They just made some computer search and then find some candidate for the minimal automata. Is Jandel and Rao paper, and then they somehow manually analyzed what is happening there and understood that from completely non-structured data, they have just the table, and they understood how it really, that it's there is some kind of transformation and compression and Fibonacci numbers and blocks and very nice complicated structure. No, of course it goes much beyond this kind of things, because they have blocks of unlimited size and so on. But
yes.
but just if you need some examples when people can extract structure from just completely unstructured data, this looks fantastic.
Yes. It's something, I think it's something we all love to do. Also, when we're faced with a mathematics problem, then first we collect a little bit of data. We look at some examples where it works or doesn't work, to make sure we think of that as understanding the problem. And then we start to we try to see, okay, what did the positive examples have in common? What did the negative examples have in common? And this is already the process where we're starting to zip things up and trying to get rid of the information that isn't necessary for the processing, and we're trying to reduce it to the simplest form, and then that's our understanding of the problem.
So they did a lot of analysis, and part of it is computer analysis. So if you have some, like in your example, if there are some tools which can help to make automatic some part of the analysis, and if they are really useful in some cases, this would be wonderful.
Yes. So here the analysis is very straightforward. I didn't think about making tools because there's just there's one compression step, and then you just apply it wherever you see it. It's super easy to identify. It's not you don't have to identify any long range structure. It's a very small structure of four nodes connected to each other, directly connected to each other. So it's it's a cycle of four. It's a cycle of length 4 of 4 zippers facing each other. So it would be very easy to automate. But I don't have I haven't written code for it because I don't have a big set of problems like binary addition where I'm really looking to apply the algorithm.
No, you can have binary multiplication by some constant, for example. So there are some simple examples you can play with, but I don't know whether it yeah, okay. Anyway, thank you again for your talk, and we hope to hear you on some other occasion for some other reason, because it's very nice, refreshingly understandable talk, and that's very good for us.
I hope,
Thank you.
Yes.
Thank you.
Thank you very much for the opportunity to speak and to meet you. It was very nice.
Yeah. You are always welcome. So if you just want to speak about something else, just tell us, and we will provide an opportunity.
Excuse me, may I ask a completely irrelevant question? In the very beginning of the talk, you commented on your algorithm of adding natural numbers, and you told that it's substantially the same algorithm, the same classical algorithm in a different form, and this is not surprising because anyway the result should be the same. It seems that in your case it's indeed it's a fair point, but we know that for multiplication of numbers there are algorithms which do not look the same. Are there any reason to think in advance that for the sum, there is indeed no completely different algorithm? At least we don't.
Yes, that's interesting. I haven't thought much about multiplication algorithms. So multiplication has this property that a change in one bit somewhere in the input changes lots of the output, and so usually I think about systems that just have local properties. And so for me, actually binary addition, I wasn't even thinking that much about adding numbers. As you can see, I think about the bits just extending infinitely in both directions. So that's not how we usually think about well, that's not how we ever think about addition if we're actually trying to add numbers together. And for multiplication, it would become right, if we have these numbers extending infinitely in both directions, then I don't think we can determine any bits of the product. So it's a bit outside of what I'm used to thinking about. I think, yeah, with multiplication, it becomes much more related to actually the mathematics of multiplying scalar values, or with matrix multiplication, there are tricks for speeding it up for multiplying matrices. Yeah, I haven't thought about trying to speed up these more intricate algorithms where all of the input bits can affect all of the output bits. I think of it, in fact, yes, so I think of it just as well, as I say, I think of it as representing structure in the world. So I imagine if every time you open your eyes, you see what happens to be an addition problem, then what would your nervous system, what would your brain learn? How would your brain model that world? Is how I was thinking. Now, if every time you open your eyes, you see a multiplication problem, if you just see A, B, and A times B, then I think you would never learn it. I think your nervous system would never figure out that that's what's going on. But unless it was unless you had very small numbers, maybe.
Or if due to some random mutation, the neural system would learn to do Fourier transform, then this multiplication would become more natural.
That's an interesting idea. Yes, I think, well, you would certainly learn some things about the initial digits are correlated with the initial digits of the answer, and the final digits are very deterministically determine the final digits of the answer. And maybe, well, I think it would require some higher powers of pattern recognition beyond what these zippers can do to reverse engineer the multiplication algorithm. Yes, if you want to do subtraction, you use exactly the same diagram, exactly the same simplifications, because subtraction is just looking at the last two rows and determining the first row. It's exactly if every time you open your eyes you see a subtraction problem, that's exactly the same world as if every time you open your eyes you see an addition problem. And if you negate the third row of the addition problem, then you're seeing, every time you open your eyes, you're seeing three numbers that add up to 0. Right? So it's completely symmetric in the three rows. So addition and subtraction are the same. It's symmetric in the three values, and so on. So in fact, the addition problem is more general than just addition. But apart from subtraction, the generalizations don't really have names.
So it looks to me like this unzipping a kind of generalization of this would be just that if you have an area or you have some complex rules on some complex data in this area, then sometimes just, okay, what these complex rules mean for the periphery. So sometimes if this results in just some simple matching rules for the periphery, then you can forget about what was in the middle.
Yes. Yes, or what the zippers will do, if there's a bit in the middle that could be 1 or could be 0 but doesn't affect anything else, the zippers will leave a little bubble where you can choose one of those two options. So you still get the factor of 2 for the number of solutions, but you can see visually that bit has no effect on anything else. And if you don't care about the number of solutions, then you can collapse those bubbles. But then you would have to think about what you want the solutions to be representing. Yes, in these cases with the one-dimensional bit worlds, zipping the zippers together is really just reducing the window size, but in a very local way in the diagram, because each zipper represents the awareness of a bit on one side of the zipper and the lack of awareness of that bit on the side where it's zipped together.
Yes.
And so by moving the zipper, you're just extending or reducing the range of where the network is aware of that bit. And the simplification rule, where the four zippers zip themselves together, applies only in the case where the two bits are completely independent, where all four possibilities exist.
Yes.
And if you would have a probabilistic version, you would need those four paths to have probabilities that are the four terms of the product of multiplying two sums. And then you could zip it into just two zippers, which are those two sums. But then that becomes difficult to do if you don't have exact numbers. Then you have to decide when is the numbers close enough to allow you to zip all the zippers together, or when are they not close enough. But if we're thinking about a statistical model, that's the sort of decision we have to make in our brain. We see some event here. We see this could be one of several ways, and this could be one of several ways, and somehow we have to decide, are those correlated or not? And it's a tricky decision. Maybe if I have bad luck every time I leave my hat on my bed, I decide it's bad luck to leave my hat on my bed. But maybe it was just by chance. So, right, this is the sort of problem humans have all the time. So thank you for
Okay, thank you again.
for the chance to meet all of you. It's very nice. I hope to see you again.
You hope to see. Bye.
Bye. So I will try to. Misha will probably send me a link today, and I will try to download it on YouTube as usual.
Okay.
Yeah.
Okay. Great. Yeah.
Unless somebody is against this, but okay.
Okay. Great.
Thank you.
Thanks.
Thank you. Bye.